All right, so we are going to take a look at graphing rational functions. Okay, so a rational function shouldn't surprise you what it looks like. F of x equals g of x over h of x. G of x and h of x, that just means they're polynomials. So you can have quadratics in the numerator, something linear in the denominator, something to the fourth power in the numerator, something linear in the denominator, it doesn't matter. But as always with irrational stuff, the denominator cannot be 0, okay? The tricky part about graphing rational functions is unlike all of our others, they can all look very different, okay? So I just wanted to show you here what some can look like, okay? So a variety of things. But the bottom line is we generally have curves, okay? So you could have two branches, we call them branches, okay, opposite corners. You could have two branches with something going on in the middle. When that happens, the something going on in the middle is either going to look like a cubic, it doesn't mean it is a cubic, but it will look something like it, or you might have, if you have two branches, something that looks like a parabola in the middle, okay? You could have two branches that are a little more slanted than the ones on the top. You could also have something that actually looks like a line with a hole in it. That's what that circle is, it's a hole. You can also have holes in any of the other graphs, okay? And there will also be asymptotes, which I'll draw in here later. I just will talk about what they are first, okay? But again, this is just, I wanted to give you a general idea of what they can look like. You will not be allowed to use your graphing calculator to graph these, okay? So we'll talk about the easiest way to figure out the shapes of the curves, okay? All right, so we're going to graph this one first. If you don't have your calculator out, that's fine. I'm just going to quickly graph it.
So on the test, there's going to be like two parts to it.
Or you won't use a graphing calculator for the whole thing, because you won't need a graphing. You can use a scientific. It's fine. Okay. So if we take a look at this graph, let me just scoot this over a little bit. You can graph it yourself, but this is what it looks like. Let's go back here. Okay. Why do you think this rational function is going to look like a line? How does that happen? Any ideas why this one is going to be a line? If you look carefully at the equation, what do you think is happening? Aiden.
The bottom's canceled out.
The bottom canceled out? Let's see if he's right. Okay, my graph's going to disappear, but we'll come back to it. Let's see what happens. So if we take the top and factor it, right? And we also factor the bottom. Right, Aiden's exactly right. These guys cancel, right? And what we're left with, x plus 2 over 2, but that's really a line, right? Isn't that the same as 1/2 x plus 1? Okay? So what happened is because those things canceled out, what we're left with is, again, the graph of a line. But then why couldn't we just write the equation of a line? Do you think there's any problems on this graph? Jack?
There's a hole at point 1, 1, 0.
Okay, there's a hole where?
Where n x equals 1.
Where x equals?
1. Oh, negative.
Negative 1, right. Remember what we talked about with our excluded values when we were simplifying and stuff, that you always have to find your excluded values before you cancel stuff out, right? So we know that x cannot be negative 1. So just to show you, if we go to our calculator again here, if I try to calculate the value when x is negative 1, my calculator is going to give me a blank value for y. Your calculator can't draw a hole, okay? So it just doesn't exist there. So that's when you get a hole, okay? And we'll write this down in a minute. But the idea, again, is that when you have a rational function where once things are factored, you get something that cancels. A factor will cancel out in the top and bottom that has a variable, okay? We will get a hole at that value. And that's what it says right on the next page here. Okay, so simplifying a rational function with a factor that cancels in the denominator. Again, if you cancel out like a 3 and a 3, that's not going to give you a hole. Okay, it has to have a variable. And again, that will give you a hole, or sometimes they call it a point of discontinuity. Okay, so there are times when, again, there's a hole in the graph, and then there are times when we have what we're going to call asymptotes. And we'll talk about how to get both of those things. Okay, so there are three types of asymptotes that we're going to be looking at, okay? Vertical, horizontal. You guys already know what those are because we've talked about them with our exponentials and logs, right? So vertical asymptote, again, it's a line where the graph will never cross, ever. Why can the graph never cross a vertical asymptote? How do we find vertical asymptotes, generally speaking? Louis?
Is it usually just like in the equations, it's just like the last number, which has like plus like 5?
You're linking it directly to exponential or log, so it's sort of. Think about our rational functions for a second. When do you think, we haven't talked about it, when do you think a vertical asymptote would occur? Barbara?
Like whatever the bottom is, if it's equal to 0, like the number that makes the bottom equal.
Right. Your excluded values. Okay, because remember, your denominators are not allowed to be 0. So that's why it can never cross over that vertical asymptote. Okay, and we'll talk a little more specifically in a few minutes, but where your excluded values are, one of two things happen. You either have a vertical asymptote there, okay, or if it was like the last example where the factor completely cancels out, we don't get an asymptote, we have a hole. Okay, so your excluded values either give you a hole or an asymptote. A hole if the factor canceled, an asymptote if it doesn't cancel. And that's written out more later as well, that's all written down, okay? Horizontal asymptote, again, horizontal line. And this, what happens here, it's interesting, is for the horizontal asymptote, it's where the ends of the graph approach. Most often, your graph does not cross the horizontal asymptote, but it can. Okay, it's allowed to cross the horizontal asymptote. It's not a value that's undefined. It's just at the ends of your graph, the value it approaches. That's why it's allowed to cross over. Okay, we'll look at some examples of that in a few minutes. And then the last type is what we call oblique or slant asymptote. Means exactly the same thing. The words are interchangeable. And that's just not vertical or horizontal, but it's still a line that at the ends, the graph will approach that value. Okay? So I'm going to go back to the very first page with the examples of the graphs. So I'm going to sketch in some of the asymptotes so you can see what they look like. Okay? So back on the first page with our graphs here, this first graph has a horizontal asymptote and a vertical asymptote. Oops. Okay. And we will talk about how to find them, okay? But just so you can see what they look like. Our second graph has a horizontal asymptote and it has two vertical asymptotes. Okay. Third graph, no asymptote, it just has this open circle. That's how you plot a hole, an open circle at that value, okay? Moving on to the bottom area. It's not gonna go down for me. This one on the left has a vertical asymptote. It's not oriented very well here, that's all right. And a slant asymptote. Okay, again, it's not supposed to necessarily cross over. I have to reorient this, I think, a little bit. And then the last one, what do you think? How many vertical asymptotes do you think that last one has? Yeah. Here, one here. Do you think it has a horizontal one?
Yeah.
Yeah. Oops. Okay. Okay, so again, you can also have, by the way, any of these four graphs on the left, they can also have holes. You can have holes and asymptotes together, okay? It doesn't have to be necessarily one or the other. All right, I'm going to scoot back to how do we find these things. So move this up a tinge. So how to find asymptotes or holes. So we're going to start with the vertical ones. Because the vertical asymptotes and the holes, you're going to basically try to find them at the same time. So let me give you an example, okay? And I'm going to start off with it already factored. It's just easier to look at it that way. Let's say we have something like x plus 2 over x plus 4 times x minus 5. That's our function. And we'll do one more, x plus 2. Okay. So everything's factored. The next thing you're going to want to take a look at is, what are your excluded values? Who can tell us what our excluded values should be? X cannot be, Bama? Good, okay? Once you find your excluded values, you just have to decide, are these excluded values going to give you a whole or an asymptote? So now we're going to look, do any factors cancel? Dealer.
X plus 2.
Yeah, since the x plus 2's actually cancel out, that means the negative 2 will give us a whole. And if you're going to plot a whole, you need its full ordered pair. So x is negative 2. To find the y value, you're going to plug into your function, but plug into the simplified function. Otherwise, you're going to get something undefined, right? So because our numerator completely canceled, I'm just going to put a 1 here to make this a little easier for us to look at. If we plug in a 2 here, negative 2 rather, we have positive 2 on the bottom, times, what's negative 2 minus 5? Negative 7. So positive 2 times negative 7, negative 14, but it's in the denominator, right? So negative 1/14. And you would approximate that the best you can, but when you plot it, you would use an open circle. Okay? And that's written down later as well. So, the whole's done. We have 2 other excluded values. Are they going to be wholes or asymptotes? Asymptotes. And again, they're vertical, right? So our vertical asymptotes will be x equals negative 4 and 5. These are lines. X equals. You can separate it with commas. You can write out x equals twice. It's all good, okay? So each excluded value must be represented either by a whole or by an asymptote. It cannot be both things.
Which one? How'd you get negative 1? Sure.
Oh, we just plugged in, to get that negative 1/14, you plug in negative 2 into the simplified function.
Oh, okay.
Okay? Questions on finding a whole or a vertical asymptote? Okay, and again, as you can see here, you can have multiple vertical asymptotes with holes. You might just have a hole. You might just have asymptotes. You might not have either of those things. Most often you have at least one of them. Okay, so that's vertical. Horizontal. So horizontal asymptotes, you have to do a little memorizing here. And it's all about what we call degree. So degree is what is the highest power. So I'm going to actually put in an example in each spot here. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will be y equals 0. So that could look something like this. I'll make it pretty simple. Degree of the numerator, I'll just put x in the numerator, has to be less than the degree of the denominator. So your denominator has to be at least something squared. Okay? Degree of the numerator is less than the degree of the denominator. Our horizontal asymptote will be y equals 0. Second option, if the degree of the numerator is greater than the degree of the denominator. So again, simple example, you could say something like, I don't know, x to the third plus 1 over x. As long as the degree of the top is bigger than the degree of the bottom, there will be no horizontal asymptote. It's possible we don't have one of those, okay? And then the last one here, if the degree of the numerator equals the degree of the denominator, your horizontal asymptote will be y equals, and it's going to be a number, okay? And you're going to use the leading coefficient from the numerator over the leading coefficient of the denominator. What does that mean? It means the number that's attached to the highest power. That's your leading coefficient. So something like 3x to the third minus 2 over 2x to the third. Same exact degree in the top and bottom. The leading coefficient in the numerator is 3. So it's going to be y equals 3 over our leading coefficient in the denominator is 2. So the only thing you have to be careful of, you want to make sure that the polynomials in your numerator and denominator are in standard form, right? Biggest power to smallest power, so you're looking at it in that way. Yes?
If you can factor out a number, would you have to like factor it out? And then...
It would still, if you factor it out, it's still considered the leading coefficient. So this is where, if you look at the very top, you want to think about the function actually in non-factored form. It'll be easier to think about degree, and then if you have to deal with the coefficients, they're not factored out. You don't want them to be factored out. Okay? So again, your only option here is you have to memorize the 3 options, right? So again, one option, degree of the numerator less than the degree of the denominator, y equals 0. Second option, degree of the top bigger than the bottom, no horizontal asymptote. Or if the degrees are exactly the same, it's the leading coefficient of the numerator over the denominator's leading coefficient. Questions there? Okay. So the last type of asymptote is our slant asymptote. Okay. Now these guys happens when the degree of the numerator, bless you, is exactly 1 more than the degree of the denominator. So the first thing I'm going to ask you is this. If the degree of the numerator is exactly 1 more than the degree of the denominator, is there a horizontal asymptote? I know we kind of move forward with the notes, so think about this for a second, right? If the degree of the numerator is exactly 1 more than the degree of the denominator, so in other words, the numerator's degree is bigger than the denominator's, is there a horizontal asymptote? No. Okay, so you cannot have a slant asymptote and a horizontal one. It's going to be one or the other. So if your degree of the numerator is bigger than the denominator's degree, you definitely do not have a horizontal one. You might have a slant asymptote if the degree is exactly 1 more. Okay, so let me give you an example, and then we'll talk about the fact that if your degree is always 1 more, then, let me just write this down. If your degree is always 1 more, if you actually did the division here, you'd always end up with something linear, right? If you have a 3rd power over a 2nd power, you divide, you get just x. If you have a 5th power over a 4th power, you still end up with an x. So that is why our slant asymptotes are always linear, okay? And the way to find them is to literally do the division. And you disregard the remainder. It's just the polynomial piece. Okay, so there might be times where you think you can do synthetic division. Like in this case, you could, because we would be dividing by something linear. But most often, you have to do long division. So that's how I'm going to do this one, okay, just to remind you how to do it. So x squared minus 1, account for placeholders. X squared plus 0x minus 1 divided by x plus 2. All right, so yeah, let's go back to our polynomial unit. Remember how to do this? So you're trying to match the x squared here. What times x is x squared? X. Multiply, so x squared plus 2x. Subtract and watch your signs, right? X squared minus x squared cancels. 0 minus 2. Negative 2x. Yep, bring down the negative 1. Now, what times x is negative 2x? Negative 2. You really don't have to go any further because this is the linear part, right? But just to remind you, if you did multiply, you'd have negative 2x minus 4. You can continue to subtract. You get 3 as a remainder, but that doesn't matter. The equation for your asymptote would be y equals x minus 2. You just take this polynomial portion to get your slant asymptote. So as soon as you pop up that constant number, you don't have to bother doing the rest. I mean, you can, of course, do the rest, but you don't need to because you're done. Okay? So again, the slant happens if the degree of the top is exactly 1 more than the degree of the bottom. All right. we are basically ready to graph. Okay? Now, in terms of graphing and making sure that you have everything you need and to do the least amount of work possible to make the graph look good enough, my suggestion is to find all the asymptotes first. We're going to graph them with a dashed line. Graph any holes with an open circle. Once you do that, we can find our x and y intercepts, if they exist. You might have multiple x-intercepts. You might have none. Remember, you can only have at most one y-intercept. Otherwise, it's not a function. And once you do that, you'll see as we start working this out, you actually may already have everything you need to sketch the branches, because we'll talk about our options. Or you might have to pick, I'm going to say at most 2 points to figure out where you're going to sketch your stuff. It's not that many extra points you will need. Okay? And again, there's no graphing calculator. So it's really going to be about accurately sketching asymptotes, holes, intercepts, and then getting enough information to sketch the branches. The branches don't have to be like perfectly perfect, if that makes sense, okay? So, let's try. All right, first example here. Remember, you also want to make sure you would factor everything first if necessary. There is nothing to factor in our first example. So, holes. You ask yourself the question, are there any factors that are going to cancel out in the numerator and denominator? No. So there are no holes. And write the word none or no or something so that I know you actually answered the question. Don't leave it blank, because then I'll think you don't know the answer. Okay. Vertical asymptote. Raise your hand if you can give us the vertical asymptote here. Paul? Yeah. Remember, your vertical asymptote comes from your excluded value. Our denominator, x cannot be 6, which means your vertical asymptote is x equals 6. All right, horizontal asymptote. So I know we don't have those notes right in front of us. So remember, horizontal, it's about degree. If the degree of the top is bigger than the bottom, there are no horizontal asymptotes. What's going on with the degree here? Bottom's bigger. So if the top's degree is less than the bottom's degree, what is the horizontal asymptote?
0.
Yes, and again, it's a line, so y equals 0. If there is a horizontal asymptote, can there be a slant?
No.
Nope. So again, nope, none. Now, you can find the intercepts now if you like, or we can start graphing. It's up to you. I guess we could just find them right now. X-intercept. That happens when y equals 0. And we've done intercepts with these functions before, earlier in the year. Is there an x-intercept?
No.
No. Remember, the shortcut version when we're talking about rational functions, what makes the fraction 0 is if the numerator is 0. So what makes the numerator 0? Nothing, right? Because it's just the number 2. So there are no x-intercepts. Y-intercept is when x is 0. Right, ordered pair, so 0, negative 1/3. Okay. Now, when you're finding the y-intercept, if you were able to factor stuff, it's always easiest to look at your original to find the x-intercept, because all the x stuff just drops right out. Just a little note there. Domain and range, we're going to wait until we graph. Okay. Now, honestly, though, domain, you can always find the domain without even graphing, because your domain is all real numbers except whatever your excluded values are. And we already know our excluded values. So actually, we could find our domain right now. Who can give us the domain? Aiden.
Infinity 6 and 6 infinity.
Perfect. Okay, so you can wait to graph if you'd like, but you can also just use your excluded value, which if you want to write that on the top just so you have it for reference, you have it there. Okay, so let's take a look at the graph. All right, so what have we got here? We have a vertical asymptote at x equals 6. I'm going to use a different color here. You don't have to use a different color. but dashed lines. Okay, so x equals 6. 1, 2, 3, 4, 5, 6. And our horizontal asymptote is y equals 0. So when it's on the axis, either extend it past, or even if you put it just a tinge above it, just so I can tell that you actually have the asymptote there. If you notice, we now have 4 sections of the graph, right? Because we have the vertical and the horizontal. When you have 4 sections like this, you will end up with 2 branches. The branches could either be diagonal from each other in either way, or they can be 2 on top or 2 on bottom. Why is it we would never be able to have one branch above the other?
Because then it wouldn't be a function.
Then it would not be a function. Okay, so we're going to look at where the y-intercept is and see if that gives us any indication. Our y-intercept is 0, negative 1/3. So just plot it, as best you can. And actually, that helps us quite a bit. This point is in that lower left-hand quadrant. That tells us that's where one of our branches is. I don't need you to be any more specific except to know where it is, and then we're going to sketch. Your branches are just curves that hug the asymptotes. And literally, just sketch it as best you can. So you're going to kind of hug that asymptote, go through the point, and hug this one. You don't need any more points than that to sketch the branch. Okay? So now the only thing we have to figure out is the other branch diagonal over here, or is it next to it down here? And how are we going to do that? How can we decide which one it's in? Yeah, pick a point. And all you have to do is look at that vertical asymptote. It's x equals 6. Pick any point to the right. And then just figure out where its y value is going to be, right? And because our asymptote is actually y equals 0, I don't even need to know the numeric value. I just need to know if it's positive or negative. And that would tell me where it goes. But let's decide. So let's pick a point. What point do you want to pick for x?
7.
7, okay? So if we pick x to be 7, pop it into your equation, right? So 2 over 7 minus 6 gives us 2. So the point 7, 2 is on our graph, which means that our other branch has to be up here. So again, just sketch. Hug your asymptotes through the point, and that's it, okay? So your branches really don't have to be graphed that accurately in terms of having a lot of points. As soon as you can identify where it is, you can sketch, okay? So not so bad. Questions there? Okay, let's try another one. Oh, range first. Range first. Look at the graph. You're going to get the range from the graph. Who thinks they can give us the range? Aiden?
Like infinity, 0, infinity.
Yes. So negative infinity to 0, union 0 to infinity. There will be some times where I will tell you not to find the range. Because we are not using your calculators, I think the next one you'll see, you won't be able to find the range, and that's fine. All right, let's take a look at this one. What should we do first? Barbara? Yeah, let's factor that denominator. How does that denominator factor? Alex?
X minus 2, x plus 3.
X minus 2, x plus 3. Yep. Okay. Now let's find all the stuff. Do any factors cancel out? No. So we know there are no holes, right? So all of our excluded values will give us asymptotes. Since there are 2 excluded values, we have to have 2 vertical asymptotes. Who can tell us what they are? Izzy?
2 and negative 3.
Yeah, so x equals 2 and negative 3. Horizontal asymptotes, yay or nay? Yes. What will it be?
0.
Right, y equals 0 again, right? Because our degree of our numerator is less than the degree of the denominator. Are there any slant asymptotes?
No.
No. X x-intercepts? None. Same problem as last time, right? If there's no variable in the numerator, it will always be none, right? So none. Y-intercept, again, I think if you look at the original problem before you factor it, it's easier to find the y-intercept because all the x stuff cancels out. What is our y-intercept? Raise your hand because I can't tell who's talking. I think someone was saying it. Louis,
Negative 706.
give me an ordered pair.
Oh, sorry, 0 and then comma negative 706.
Yeah, good. And while we're here, because we can, let's find our domain. Alex?
-3, -3, Newman, -3 to 2, Newman 2 to infinity.
Yep. Remember, you're always going to have one more section to your domain than excluded values. If you have 2 excluded values, you're going to have 3 different intervals for your domain. Okay? Range we're going to leave for right now. All right, let's give this one a shot here. All right, let's see what we got here. Vertical asymptote at x equals -3. Vertical asymptote at x equals 2. Horizontal asymptote at y equals 0. All right. So there's more happening in this graph than the other one. When you have 2 vertical asymptotes, you will always have 2 branches on the outskirts. So on the left and the right side, you'll have 2 branches. Either they're going to be both in the top, both in the bottom, or diagonal, okay? And then in the middle is where you'll have either that thing that looks like a cubic or something that looks like a quadratic, okay? So I always like to figure out the branches first. I'll tell you why once we find them. Let's see if our ordered pairs help us in this case. Our y-intercept is 0, -7/6. So nope, that's not going to help us with our branches. Yeah, they'll help us with the middle, but not the branch part. So that means we need to find out what's happening to the left of our vertical asymptote at x equals -3. How are we going to figure that out? Plug in, okay? So pick a point that's more negative than -3.
-4.
Okay. So if you plug in -4 for x, whether you need to use your calculators or you're doing it in your head or whatever, let's find the value for y, or at the very least whether it's positive or negative. Because again, since our horizontal asymptote is at 0, we just want to know, is it above or below that line? So take a minute, raise your hand when you know where it's going to be. Nick, you got something for us? -1.
Oh wait, no, positive one.
Positive 1? Like you're saying the answer is going to be 1 if you plug it in?
Oh no, I mean like. Alright, so plugging -4, right?
Yeah.
Yeah, so -2. Oh wait. Oh, okay. Just kidding.
It's okay.
Alright.
Basically, you have 16, right, plus -4, which is
Oh,
12.
6.
12 minus 6? 6. 7/6. Now, again, the actual point doesn't matter so much. What matters is that it's positive in this case. So -4, positive 7/6, it's somewhere over here. It's fine. But the important thing is it's in this upper left-hand quadrant. So sketch. Hug the asymptotes, make your curve. If you didn't bother to find the actual value, but you just in your head knew it would be positive, fine. Then you're not going to have a point up here. You're just going to sketch the branch. I'm okay with that. Right side. We need to know what's happening to the right of that vertical asymptote of x equals 2. Pick something bigger than 2. Okay, we picked 3. I'll just go back over here. Again, you decide. You can find the actual value or decide if it's positive or negative. Jack?
It's positive.
It's positive. Okay, did anyone find the value? Just curious. It's actually, strangely enough, it's the same value. It doesn't always happen that way, okay? But again, knowing it's positive is enough. If you just figured it was positive, you could just sketch your branch right away. Now that I know it's 7,6, I'm just going to actually kind of plot it a little bit here. And again, just sketch your branches. Okay, so we've got two branches that are next to each other. Every time that happens, the stuff in the middle is going to look like a parabola. Yep, and because our y-intercept told us it was down in the bottom, that's where it will be. And again, these can all look a little interesting. I am fine, because we're not using your calculators, whoops, okay? Just sketch something that looks like a parabola in the middle. It's totally fine. You don't have to kill yourself making a lot of points here, okay? If the two branches were opposites, the middle would be something that looked like a cubic. Okay, and we'll do one of those too so you can see how that looks. You can always pick more points if you want, but this is like the minimum that you would need to do. Okay? Are we okay here? All right.
Oh, you guys didn't do the range.
Oh, thank you. I keep skipping that. The range. This is one that you actually can't find. Only because we're not using our calculators. Because what would you need to know? You would need to know this maximum point here, whatever it is, right? Without knowing where it stops here, you don't know where to tell it to go. So I wouldn't ask you for the range. If you had your calculator, you could do that maximum value on your calculator. But we don't have them for this. Okay, so we're not going to find the range. Okay, so if this were an assessment, I would tell you, I would just leave it off. Okay?
Isn't it just the y?
People would ask
It might not be. It could go up a little higher. Remember, it's not necessarily.
If she left us a range box, people would be asking why there's no range box.
Okay. Next one. I want you guys to find all the stuff right now. Find everything but the range. If you need to talk with your partner, go for it. Okay, we're finding everything but the range.
There is no.
There is a range.
Oh, this is one more.
So there's no. Vertical C one, right?
I've got. Wait. I have.
So no, it's not.
No, I meant like mine. Is there a slant? Yes.
What is this?
You have to divide all of them.
45 seconds. You can do it.
I do not know.
Oh, wait.
I'm going to give you another 30 seconds. You guys are still working, it looks like.
Are you graphing it as well, or?
And don't graph it, just find the stuff. I want to make sure everyone has that correct.
It's minus 1. Plus 1. No, do it again.
The other one?
When you subtract, just make sure you watch your sign, so that's why you say change your value.
Oh no, that's horizontal.
Oh, you.
What'd you say it was?
Um,
Alright, let's take a look. Is there anything that can be factored? No. X squared plus 1 cannot be factored. No holes, right? Who can give us the vertical asymptote?
X equals 1.
X equals 1. Horizontal asymptotes?
X.
None, right? Because the top degree is bigger than the bottom degree. And in fact, it's exactly 1 bigger. So this means we are going to have a slant asymptote. So you have to do your long division. Who can give us the equation of our slant asymptote? Obama? Yes. Y equals x plus 1. We'll come back if you need to see it. Let's just keep going for right now. X-intercept, or septs. None. There are no complex intercepts, right? So x squared plus 1 equals 0, nothing. Okay, so none. Y-intercept. Jack?
0, -1.
Okay, we'll get the domain and then we'll see if there's questions on getting any of that stuff before we graph. You can give us the domain. Use your excluded value. Nick? Okay. All right. Anyone need to see how to get any of those things? You guys are okay with the slant, Mama?
So for the x-intercept, you just make the numerator equal to 0.
Yeah.
Okay.
Yep. Anything else? All right, let's take a look at the graph. Vertical asymptote, x equals 1. You guys should all know how to graph a line here for the slant asymptote, right? Our y-intercept is 0, 1. Use your slope, up 1 over 1, up 1 over 1, down 1 over 1. Just get enough points that you can get a decent look at your line here. Okay, now, slant asymptote still gives you 4 regions, just like having 1 vertical and 1 horizontal does. It's just that it's slanted. So the same thing's going to happen. You're going to have branches in 2 out of the 4. They can never be above and below each other. We have 1 intercept, so let's see if that helps us at all. 0, -1. That does help us. That tells us we have a branch down here in the bottom. So again, hug the asymptotes, go through the point. Okay? How high up you go, whatever. I mean, again, the point is we know where it is in terms of which section. So what that's going to tell us is that there will be no other x value to the left of the vertical asymptote that will be part of our graph, right? Because that would make the branch, next to it, or I should say above it. So we need to know what's going on to the right of that vertical asymptote. So pick something bigger than 1. Paul? 2. If we plug in 2, 2 squared is 4, 4 plus 1 is 5. If we plug in 2 on the bottom, 2 minus 1 is 1. Our point is 2, 5. So 2, 5 is going to be up here in the tippy top area. 1, 2, 3. I'm off my spot, so I'm just going to graph it like this. Okay, again, you can plot the point if you had some room up there. I'm out of room. So it's going to be in that upper, that upper diagonally from the one on the bottom. Hug the branches. You're good to go. Okay. So it should be a little higher on mine because I have the actual point, but I'm out of room. Are we okay there? Can we find the range? No. And again, for that same reason, if you had your calculators, you could find the max and the min, and you'd be able to do it. Okay, but we cannot. So don't find the range here either. All right. We have just enough time to do this last one. We're going to kind of do this one together just, again, for the sake of time. So let's factor our numerator. X, and what's going to factor the numerator here?
Minus 3 minus 1.
Right, minus 1 and minus 3 in there? Okay. Denominator, we can take out a -2. Oh, so I can actually keep going, can't I? Right? So we keep our x minus 1, x minus 3 in the numerator. Our denominator, we can continue to factor our difference of squares. Okay. Does anything cancel?
No.
Nope. So we haven't done any with the whole. You guys will do those on Monday. They'll show up there. Okay. Vertical asymptotes. How many will we have? 2. Yes. Who can give them to us? X equals
2 plus minus 2.
2 or -2. You could write plus or minus 2 if you want to write it that way. Fine. Horizontal. Look at the non-factored form. Okay, that's where you want to look. So you can easily see your degree and, if necessary, coefficients. The degrees are the same, right? So this is one of those where you're going to have the leading coefficient from the numerator, which is 1, over the leading coefficient from the denominator, which is -2. So -1/2 is the horizontal asymptote. Is there a slant? Nope. Okay. X-intercepts. There are 2.
Yep. 1 and 3.
1 and 3. So 1, 0, 3, 0. Okay. I would look at the factored form to help you with those. The y-intercept, the non-factored form, is usually easiest. What would our y-intercept be? 0. All the x stuff cancels out. We're left with 3/8. Okay. Domain. -infinity to -2. Union. -2 to 2. Union 2 to infinity. And we're going to hold off on the range. All right, we got a lot of stuff here. All right, asymptotes. 2 and -2 for x. Oops. Y equals -1/2. Okay, so as best you can, sketch that out. Let's look at our points and see if they help us at all. X-intercept, 1, 0, which is here, and 3, 0, 1, 2, 3, 0, which is here. Okay. The 3, 0 helps us out, right? Because that's going to tell us I'm going to have a branch right here. Hug the asymptotes. There we go. I don't know what to do in the middle yet, so I'm going to wait on that. Let's see what's happening to the left of our other vertical asymptote. So let's say you plug in -3 or something like that, right? So use your calculator if you need to. Figure out the value. Tell me if it's above or below -1/2. That's all we need to know. Paul? Negative? But is it negative? Is it going to be more negative than -1/2?
It's less negative.
Oh wait.
It's more negative, right? So it's going to be down here. Yes? All right, so down here, hug the branches. Because our branches are opposites, that means the stuff inside this middle is going to act like a cubic. Oops, I missed the point. it should go through there. I'll make that really thick right there. Okay, again, and it's allowed to go through the horizontal asymptote. We talked about that. If you really want to know what that point is, you can set your equation your original equation, equal to the value of the horizontal asymptote, and it will give you the value for x. Yeah.
Can I like flip sometimes like a cubic lie.
Yes, it could do that too. So you could pick another point to double check yourself. Okay?
Wouldn't it be like flip because the y is 0?
What did I miss?
Like, well,
Oh, 0.3/8. I forgot about that point. That's over here. Oh, wait, whoa. Thank you. Yes, Alex. Good. Yes, wait. Oh, this is erasing is problematic. Oh, terrible. We didn't plot the y-intercept. So 0.3/8 is here, right? Sorry about that. 1, 0 was here. It actually should go like this. Thank you. Okay? Phew. All right, guys. So your homework is that one sheet. You're just finding all the stuff.